Welcome to this explainer. Okay, today we're going to demystify the completely invisible mechanics running the modern world. Seriously, think about it for a second. The smartphone in your pocket, the electric vehicle silently gliding down your street, even the massive servers keeping your favorite websites online right now, none of that would work without a hidden, relentless translation of electrical energy happening behind the scenes. Today, we're talking about the mechanics of power conversion.
It all starts with this core problem. Have you ever wondered why you can't just plug a battery straight into the power grid? No way, right? It would be a total disaster. The answer is that the electrical grid and your modern electronic devices speak two entirely different, totally incompatible electrical languages. The grid speaks in alternating current, or AC, while your devices and batteries speak in direct current, or DC. Bridging that massive gap is exactly what this explainer is all about.
Okay, let's dive right into this. We'll start by looking at the power translation problem, then check out converters going from AC to DC, and inverters going from DC to AC. After that, we'll put them in a head-to-head matchup, and finally, we'll see what happens when they work together in a VFD.
Section 1. The power translation problem.
So, if you've ever heard folks throw around the terms converter and inverter interchangeably like they're the exact same thing, well, in power electronics, that's actually a pretty big mistake. While the word converter is technically this broad umbrella term for any device that changes energy from one form to another, the industry standard is super specific. When engineers talk about a converter in this context, they mean an AC to DC device. It's specifically known as a rectifier, and its only job is grabbing that power from the grid and transforming it into direct current.
Now, an inverter, that is the strict exact opposite. It takes that direct current, or DC, and transforms it right back into alternating current, AC. They are basically mirror images of each other in the electronics world. And honestly, grasping this structural mirror concept is absolutely crucial to understanding how our entire modern electrical infrastructure operates.
Section 2. Converters, going from AC to DC.
Let's actually look at how we tame those wild, oscillating waves of the public grid. It's kind of like a mini adventure. First, in step 1, that alternating AC wave enters the circuit, constantly rising and falling. Then, in step 2, these semiconductor devices, things like diodes or thyristors, they act exactly like one-way turnstiles for electricity. They literally physically block the negative half of the AC wave, forcing all those electrons to march in one single direction. Finally, in step 3, components like capacitors and inductors act as shock absorbers. They smooth out all that bumpy, pulsating energy into a perfectly flat, steady line of DC voltage.
And you know, the real beauty of this setup is why it's so advantageous. This process of rectification relies on relatively simple, incredibly robust, and primarily passive circuitry. Because it's so efficient, it reliably lets the high-voltage, crazy alternating power from the grid safely run the super-sensitive, battery-driven electronics we use literally every single day.
And when I say every day, I mean it. You're surrounded by converters right now. They're tucked inside those little charging blocks for your phone and your PC. They're hidden inside your household electronics. On a massive scale, they're the input stages for giant industrial battery chargers and UPS systems, and they're even used in massive high-voltage direct current transmission stations. Basically, if it has a battery, it absolutely needs a converter to interface with the wall outlet.
Section 3. Inverters, going from DC to AC.
All right, let's flip the script. We've seen how to get power into a battery, but what happens when we need to go the other way? Unlike the smooth, passive absorption of a converter, the inverter is this highly active, incredibly fast-paced device. So, step 1, DC power flows in as a continuous, straight line. But to create AC, we jump to step 2, where solid-state switches, components with intense names like IGBTs or MOSFETs, violently open and close thousands of times per second. Thousands! They're rapidly reversing the direction of the DC voltage. Then, in step 3, this brilliant control logic called pulse width modulation, or PWM, carefully shapes those rapid-fire pulses so they perfectly mimic the smooth, oscillating wave of AC power. It's a high-speed digital magic trick creating an analog wave.
This highly active process is totally vital because it gives us precise control over both the frequency and the voltage of the output. We're not just blindly dumping power back into the wall. It's about active, intelligent control logic. And that is absolutely critical for seamlessly tying into the public grid and for controlling the speed of massive electrical motors.
This is exactly why inverters are the absolute backbone of the green energy revolution and modern infrastructure.
Think about a solar roof. Sunlight hits the panels and creates DC power, but an inverter is what translates that into grid-tied AC power for your house. In an electric vehicle, the giant DC battery relies on an inverter to translate that power to run the AC motor spinning your wheels. And if the grid ever goes down, the output stage of an uninterruptible power supply, yep, an inverter, turns that battery backup power into AC to keep critical internet servers alive.
Section 4. The head-to-head matchup.
And this brilliantly illustrates the whole dynamic. Bringing both of these devices side by side is for sure the absolute best way to lock in everything we've learned. Just look at the outputs. The converter's output is like a calm, perfectly flat, continuous straight line of DC power. The inverter's output, on the other hand, is a highly dynamic oscillating wave, whether that's a pure sine wave, a square wave, or a modified sine wave of AC power. So it's calm and straight versus dynamic and waving.
When we map it all out like this, the distinctions become super clear. For energy flow, converters push power from the grid to your batteries, while inverters push power from your batteries or renewables back to the grid or to your motors. For components, converters use those passive one-way valves we talked about, diodes and thyristors. Inverters, they rely on the high-speed switching of transistors and oscillators. And regarding complexity, the converter is generally a simpler, passive process of rectification, whereas the inverter needs complex, active control circuits using pulse-width modulation to literally build those waveforms from scratch.
Section 5. Working together in the VFD.
Okay, here is where things get truly fascinating. What happens when you smash the passive rectification of the converter together with the active high-speed switching of the inverter? You get a variable frequency drive, or a VFD. It's essentially the ultimate team-up of these opposite devices, allowing engineers to gain absolute total control over industrial motor speeds. Here's how the energy flows. First, the front-end converter takes the rigid, incoming grid AC and flattens it out into a stable, continuous DC bus. Then, it feeds that straight line directly into the back-end inverter. The inverter takes that steady DC and chops it up, pulsing it using PWM to create a brand new, totally customized AC output with a variable frequency. By pairing them together, we literally take inflexible grid power, strip it down, and rebuild it into totally customizable mechanical power. How cool is that? So as we wrap up this explainer, I really want to leave you with this thought. We live in a world that is fundamentally split between the AC power of the massive grid and the DC power of our digital, battery-driven lives. These continuous, invisible translations are happening all around you, thousands of times a second, making modern life possible. So taking a look around your house, or your driveway, or your office, where will you spot the next converter or inverter in your own life? Thanks so much for exploring the incredible mechanics of power conversion with us today.